Okay, hello everybody. Don't be intimidated. We're going to take a look at R, the statistical package that is used all over the world by scientists and researchers, and which is open source and free, unlike much of the other software like SPSS or SAS, which can be very expensive, and once you leave the university, if you don't have somebody paying for it, then you lose access to it. So here you invest your time learning in R, and then you can use it for the rest of your life and develop. So when you are getting R, you will find it as the R project for statistical computing, and you can click on that, and then you can download R from here. To download R, and it will look like this, and you pick one of these mirrors. I picked there, and I clicked on it, and I downloaded it. All right, so that's just a typical thing. Then I click on it, and I open it up, and this is the first thing I see. I see this console. R is what you see is what you want to get program, not a WYSIWYG, or what you see is what you get. It's what you see is what you want. Like LIX and LaTeX, MikTeX, BibTeX, the computer does the processing and the formatting, and you give commands to tell the computer what to do. And that can intimidate some of you. I know it did me, but you get used to it. So let's get used to it, and let's jump right in. A couple of things. You can use R right out the box, but they do have these things called packages. And when you go to install package, it will say select a mirror, a CRAN mirror for use in this session. Doesn't matter where you get it, India, Indonesia, but I'm going to pick the USA, and I'm going to pick California because Google's there. I don't know. So once you've picked a mirror, then it comes up with the packages, and I don't know if there's an easy way to jump through the packages. Tab doesn't seem to work, and there's no Control F for find. But some of the useful ones are ones that let you do work like with Excel, if you're doing your data in Excel spreadsheet. So go and find the Excel SX, and you can say OK, and would you like to use a personal library? Well, if you do say yes, then you install it into a personal library. So this will be in Documents R, Windows Library. So I'll say yes and install it in there. That's personal. And then it loads that in there. And another one is, I guess it's not going to let me do anything else. Okay, it did. So then go to packages, and another package that would be nice to have is the other Excel one, and they recommend putting that in. So let's go down and let us get in X down here. There is a package called Excel Connect, and these let you read and write Microsoft Excels from R, and boom, we install that one. That's to load data. There's others, but things like SQL database, and if you want to do SAS or SPSS data sets, then you'd put other things in. But I'm going to assume we're not going to do that for now. Other handy ones is to manipulate data. And let me show you where I'm getting this information from. This is the supportrstudio.com site, RStudio support, and they have the recommended packages. So another one would be there's Ggplot for subsetting, summarizing, and joining together data sets, and then there's ways of changing the layouts. So we'll go for Ggplot in this, and when you click on that, it tells you all about it and tells you how to use it. And it says here, it says that tabular data is tabular data regardless of where it lives, but it says the bottleneck in most data analysis is the time it takes you to figure out what to do with your data, and this makes it easier by having individual functions that correspond to the most common operations: group by, summarize, mutate, filter, select, and arrange. So let's get that just because. So we'll go to packages again and do install package, and let's go down and get Ggplot. And should be able to find it here for a second. So there it is, dplyr. I don't know if you can do more than one. Let's see. Yes, you can actually. So we have Ggplot. We'll just leave that selected, and let's go back here and look for others that we should have. That's to manipulate data. And let us do to visualize and model. Let's get one for each of those. So we've got a load data package, a manipulate data package. To visualize, the famous package for making beautiful graphics is Ggplot. And then there's Ggvis, interactive web-based graphics built with the grammar of graphics. Interactive 3D visualizations, that's going to be good for us because we want to do 3D. And we probably don't need the rest of this for right now. Although leaflet maps would be cool. Okay, so what I'm going to do is I'm going to go up and get Ggplot and try to find where that is. It's alphabetical, so it shouldn't be too hard. Hij, GG is there, ggstat, ggplotify, ggplot2, and they're saying ggplot2. So there's ggplot2, so I hit the control key to grab on that. And then I want also ggvis, so I can do interactive stuff. So you're setting up, it's like going shopping, you know. And then I'm going to get RGL. So RGL is there, and then we're fine. We wanted maps also, so leaflets. I think we need HTML widgets first. So we'll go back up here to HTML widgets. HY, HT, HTS, HTML widgets, and we want leaflet. So JKL. A lot of different packages for this. So people are writing them all the time. That's part of the fun. So it's a computer. So computers can do enormous things if they're programmed properly. And to have a community that's constantly solving problems is what's so exciting about this. So there's leaflet for doing that. Maybe even DY graphs for doing, well, I guess we're getting ahead of ourselves. There's so much that we can get. So let's start there. I'll accept Google Chart Tools for visualizing data that Hans Rosling made famous. Well, look at that, Gapminder, the graphing software that Hans Rosling made famous in his TED Talk. All right, so let's definitely get Google VIS, Google Visualization. Should have that. So this is what's so exciting, is going shopping in this. And this is before you've even learned how to use the program. You can see it's already getting exciting. You can be Hans Rosling. So Google VIS, there it is. There's a lot of other Google stuff here too. Google Knowledge Graph, Google Compute, Google Practice, Google Drive. So, but let's start there and let's say OK and download all these packages. All right. Okay, so we've gone shopping and it's absolutely crazy. We've downloaded all these different packages, and when we get down here, many more than just the ones that we asked for, and I guess because they're linked up and they are part like color space and stuff like that. Web shot. So there's many more packages or sub packages within the packages. I think we've got stuff installed. All right, so now we got all this stuff that we bought, and or maybe it's still working. Oh, it seems like it is still working. Oh my gosh, it's still unpacking. Okay, so JSON Light is being packed there. Scales. I just gotta wait then. You gotta wait till it unpacks, and we've gone shopping, bought all this stuff, brought it home, and we throw it on the basement floor, and then we got to figure out what we're going to do with it. Like there's Google VIS, the thing where Hans Rosling. Okay, so it already did it. So we've got that visualization, GGVIS, and Google VIS. All right. So the first thing we're going to do is we're going to plunge right in, and instead of following what most of the tutorials do and take you through basic math functions, which I consider really horribly boring, we're going to jump right into plotting in R, because that's what we want to do, and then work our way backwards to some of the simpler functions, because everything is difficult when you've never done it, and everything's simple once you have. So you don't have to have installed all these packages, but it's fun to start by going shopping. Another way you go shopping is that you can look at data sets that have already been prepared for you, so you don't have to get your own data to start with before you start using these cool tools, these cool packages. What you do is you type in, and get rid of the caps lock, type in data and just open brackets. So it's like, I want data, and you put your hands together, like open brackets. I want data here. Give me data in there. And when you hit return, you get all these data sets that are available. And there they are. Monthly airline passenger numbers, formaldehyde determination, hair and eye color of statistics students. Let's look at this. Quarterly earnings of Johnson & Johnson share. Oh, the effectiveness of insect sprays. Oh, that's a good one. The flow of the river Nile, the growth of orange trees, the growth of loblolly pine trees, seatbelts, road casualties in Great Britain from 1969 to 1984, the effect of vitamin C on tooth growth in somewhere, quarterly approval ratings of U.S. presidents. Well, that is certainly useful for the State of the Union. And annual precipitation in U.S. cities. Maybe we should look at that. That's a good one for sustainability, for climate change mitigation. And there's also monthly sunspot data, and there's fertility and socioeconomic indicators in Switzerland, tree ring data, average heights and weights for American women. That's another one, if we can relate it to diet, for example. Topographic information in the volcano. But I think I would want to choose the annual precipitation, which is precip. And so it says use data and then package equals dot packages to see all the available data sets and all the available packages. So if we wanted to do that, then we could say that. We could say date. Let me go back here, down here, and say, let's see how this works. See the other data sets that are available. Data, and then packages, all available equals true, and then close that bracket, and then see what happens, and it says, maybe I messed something up, available, all dot available. Okay, well, I didn't type it in right, so better to copy and paste. That's much better. Oh, by the way, you can do paste to console, and then it goes right in. You don't have to paste it back in, and then hit it. Okay, there we go. And we see that there's a whole bunch more of stuff like bladder cancer recurrences in package survival. In the SP, there's prediction grids, river muse outline, automobile data from Consumer Reports in a package called RPART. So all those packages actually also come with data sets. So you can do an amazing amount of work with this. Brain and body weights for 28 species of animals in the mass package. So you could do that brain size and body weight characteristic correlation if you wanted to. Mortality rates by cause and gender. And here's Google VIS example set. That's the one that we got. There is Cairo daily temperature data for Cairo, or city popularity, or exports, fruits, population, regions, dinosaur data. So maybe we should start, actually, for the fun of it, with a Google VIS data set. Maybe we'll do two. We'll do two data sets. So let's learn how to import the data set. But for starters, we got to do one data set at a time. So I'm going to load in the precipitation data that we saw, this one here. and I'll copy this, and I'm going to say over here, I'm going to type in data again, but in those parentheses that we talked about, I'm going to put in precip. And now, when I do that, it will load the data in. So then if you want to see what's in one of those data sets, then you just type in the name of that data set, and the console shows you the different cities, and it shows you the precipitation. Now, there's a couple of ways that you can go about calling out specific data. The one that most people learn is to take the data that you're looking for, precipitation, and then put a $sign and then say where you want to find it out, like Houston. Problem is that this syntax doesn't work for what they call atomic vectors, meaning it's been atomized. Like there's only one value for each of these. Houston down here somewhere, here it is, 48.2, is an atomic vector. It's just one data piece and it's not arranged. So what you do for that is you say, no, what I really want to do is go practice, precip, not practice, you do want to practice, precip, and then put brackets, double brackets, and then say Houston, and then within quotations, and then double close the bracket, and then you get that value coming right up. And so you can then say, precip, and then wherever, St. Louis, as long as you spell it properly and put in your quotations, which I did not there. And you can't get back there, so you got to go back with the arrow key and then go forward with the arrow key. And then you can see what St. Louis's precipitation is. Working with atomic vectors is a little more difficult, so I'm going to switch data sets. Let's look at a different data set that is a little bit easier to work with, that we can actually plot. And let's get a plot. So let's take a look at, for example, CO2, which is relevant to our climate classes, which is Mauna Loa's atmospheric CO2 concentration. So we type in CO2, and there is all that data arranged by month and by year. So now the problem with this data set is it's also atomic vectors, so you can't do much with it. And you'll find that out immediately if you say CO2, if you say CO2 and then $sign and then try to pick anything like the month January, it says you can't use that operator. And here as well, you'll find that it doesn't work even with the object element style where you do January like this and close those brackets as we did before. If you do that, then it says the subscript is out of bounds. So there's some data sets that these easy manipulations don't work on. Let's go to one that it actually works on, that we know it works on, but know that you can preview data this way. Sometimes it's just fun to see if you can do these simple things and get to know some of these, like student sleep data. Let's see, does that give us something that we can work with? Sleep comes up. Anything you have loaded in. So there's some sleep data, and if we then said sleep and then said $sign extra, yes, okay, so that isolates that column's data from 1 to 19, where we have 4.6 and 3.4. So it tells you where that starts. Same thing if you were to say sleep and then $sign and then group, and then we'd see the different groups. And if we said sleep and then $sign and then ID, we'd see that. If you went sleep and as the object and then put the double brackets and then said extra and then closed them, you'd get the same thing. So these syntaxes both work using the name of the data set and a $, and then the parameter that you want to isolate, or using the name of the data set and then double brackets and then put the parameter in quotes and then double brackets. You'll get the same result. This one can be used for non-atomic data, and this one can be used for atomic data unless it's out of bounds. So there's some restrictions, but good to know these tools. So think of each of these things as a tool, like a wrench or a screwdriver that you're going to use on different types of data. Now, let's see if we can do one more of these that's relevant to our sustainability, which might be, let's see if the growth of orange trees is relevant to Florida. So there we have data that we can probably work with, and we can see the growth if we say orange and then $ and then circumference, and we have isolated that. So this is the data set that we're going to work with because it works. And let's try working and getting a plot of this to see their growth in circumference by age. So here's where it begins to get exciting. We're going to plot by simply using the command plot. That's all you have to put in there. And when you have the plot command in there, then what you're going to do is you're going to pick a dependent and an independent variable. So let's do plot and then open a bracket, and then let's say that we want to plot what we want. The x is usually the independent and the y is the dependent. One depends on another. This goes to your hypotheses. You need to think of causality because that's what your hypothesis usually is, trying to explain one variable by another variable. So is age dependent on circumference, or is circumference dependent on age? So is the tree older because it's bigger, or is it bigger because it's older? And most of us in this part of the universe tend to think that age influences the growth of things rather than growth influencing the age. Time tends to flow linearly in this time-space continuum. So I would say plot and then say orange and then $, and then age, which is the independent variable. It's independent. You're going to get old anyway. And then put in a comma and then say orange, $, and then circumference. And so now it's XY being plotted. And when you do that and you hit enter, bingaloo, you get a nice little graph plotted out there, which shows that as the trees get older, moving this way on the x-axis, they also tend to get bigger. And we don't know which trees get bigger or why from this data, but we do have this plot. Now you can also come back here and plot the orange tree by the tree itself. And I don't know what good this is really going to do, but might as well try to do it. So let's say that circumference is dependent on the type of tree, the tree having a designation of some species or something. We don't know from this data set what it is. And then say orange $, circumference, and see if the circumference is dependent on the type of tree. Now if we get these whiskers, that shows that it does look like the widest trees within these whiskers. The whiskers show the range of the heights within that set, because look here, like tree number 1, which is a type I would guess, which all have different ages. Wow, one was 1,372 years old. Goodness gracious. And then you have these other trees that range from 118 years to 1,004 years. I wonder if this is in years or if this is in days. I have to imagine this is days, otherwise you'd have these Methuselah trees. And they do exist. Like there's one palm tree at the Arava Institute that It goes back to the time of Moses, I guess. But no, this has got to be days, really. That's like a year and a half there. That makes more sense. You really should know what your data is describing. But what it does look like, just looking at the range here with the bar, is that tree species number 4, even though there's a wide range, tends to get bigger than tree species number 3. As you can see, that corresponds to the data here, these little guys. But you know, are very small within tree 3, and their ages do get up there, 1,004 days, 1231. That counts for some of the other range things. We know that with age, trees get bigger, but it doesn't seem to, it also seems to be affected by the species of the tree. And that's going to have to be determined by an XYZ plot, by a 3-dimensional plot. You can't really tell that from a 2-dimensional plot. You can compare the plots and then see what you get, and then come up with other hypotheses as to why that is. So this is the great fun, that you can do this kind of work immediately. And let's just see if we can, let's look at loblolly pine trees, because that's one type of tree. So if we go to loblolly, over here, loblolly, and we've got all that data there for loblolly. Looks like they collected a huge sample set. And here we have height, age, and seed. But they do not have, in this, the size of the trees. It's not about circumference. I guess it's about the number of seeds. Oh, it's height. We can use height. So let's use as our independent variable. Let's use age again, and then let's plot height against age and see how loblolly pines do. So again, we would say plot, and we would then come up with a bracket, and we would say loblolly. I wrote that right, loblolly, and then $ age, comma, and then loblolly $height, if they spelled it like that. And there we go, we get a graph. And what do we see in this? We see that the age, as it goes up, correlates with a increase in height. Any other fun ones we can do here? The effectiveness of insect sprays. I hate insect sprays. Carbon dioxide uptake in grass plants. And biological oxygen demand. Let's do biological oxygen demand, see what that graph looks like. Okay, time and demand. Clearly that's not worth graphing, because it just sort of shows that over time the demand generally increases. That does go up and go down, so there's some interest. It's a small data set. Let's try the CO2 set. Have fun with that. All right, Mississippi, Quebec. And so we have here carbon dioxide in grass plants, and the treatment and the concentration and the uptake. So we could look at this and we could say, well, does the concentration of CO2 affect the uptake? So independent would be the concentration of CO2, and then the hypothesis would be that as the concentration of CO2 increases, then plants take up more carbon. But is that true? So here's a real life example drawn from Quebec and drawn from Mississippi, and of course there's other variables that can complicate things, whether the sample is chilled or non-chilled. But before we tease all that out, we should at least see a general trend. And what is your hypothesis? Do you think that uptake of CO2 is dependent on the concentration of the CO2? And if so, what is the causality? So again, we'd say plot. We would go here and decide that since the data is called CO2, we'd say CO2 $, and then what's the name of the variable again? Concentration, conc, and then uptake. Okay, so conc, and then comma, CO2, and then uptake. And there's our graph. And lo and behold, it seems that the concentration could be described by a line that shows a correlation with uptake. It seems that the lowest concentrations of CO2 had the lowest uptake for sure. And the highest concentrations had the highest uptake, but this enormous range here. And that's the problem. This does loosely correlate, but does it regress? Is it statistically valid? And that's when this gets scientifically interesting. How do we interpret this data set? And that's where we do a regression analysis. And that's what we'll get into next.